Okay, in this section we're going to talk about some interactions between the concept of linear dependence and spans. Now, you know the idea of span means you take a set of vectors and form all linear combinations of those vectors, and that set is called the span of those set of vectors. You know, linear dependence means that there's some linear combination of a set of vectors which gives you the zero vector. All right. Now, where these two come into interaction is that you might have two different sets of vectors that have the same span. Right. There's no thing that guarantees that two different sets of vectors will have different spans. So if you have a set of vectors, let's say v1, let's just call it v1 through vn. Okay, and these are vectors, and I take the span of this. Now, it's possible that I can remove some of these vectors and still have the same span. So the question is this set of vectors the smallest possible? Is it possible to throw out some of these vectors and still have the same span? So I can say, is this the smallest set? Is this the smallest set which gives this span? Okay. In other words, are all of these vectors necessary to get the same span of vectors? Okay, let me just give a simple example. Suppose I take two vectors, 1, 0, and 2, 0, and I consider that set of vectors, and I'll take the span of that set of vectors. Okay. Now, what you'll see is that any multiple of 1, 0 is in fact in the span. Okay. In fact, this is the same thing as the span of the set 1, 0. The 2, 0 adds nothing. Why is that? Because I can obtain 2, 0 from 1, 0 by multiplying by 2. So the 2, 0 really adds nothing. Okay. So this set here, 1, 0, 2, 0, is actually linearly dependent, and this set here is linearly independent. Okay. So we're going to again make this relationship a little bit more formal. So let's dive into the discussion. All right. So if we use a linearly dependent set to construct a span, we can always create the same infinite set, that is the same span, with a starting set that's one vector smaller in size. Okay. So what are we saying here? That if we have a linearly dependent set, then you can throw out one vector from that set without reducing the span. Okay. All right. So that's only the case if you start with a linearly dependent set. If you start with a linearly independent set, that's not possible. So in a certain sense, using a linearly independent set to make a span is the best possible way. There are no extra vectors in that linearly independent set. Okay, so let's formalize this conclusion, and you'll see how this works. This theorem, DLDS, says, suppose we have a set of vectors, and we'll see examples later to see what's going on. Then S is a linearly dependent set if and only if there is an index t between 1 and n such that ut is a linear combination of the vectors. No, see, these vectors are all the vectors except ut. So this is all the vectors except ut. So ut can be expressed as a linear combination of all the other vectors. Okay, so get the point here. If we have a set of vectors that's linearly dependent, there has to be there is at least one vector in here. It's not saying that any vector, but there's at least one vector in here that can be written as a linear combination of the other ones. So here's the proof. Now remember, this is an if and only if proof, so you have to prove it two ways. Okay. So we're going to start this way, proving the forward implication. We start with the assumption that S is a linearly dependent set. So we're starting with the assumption that these vectors are linearly dependent. Okay, so suppose S is linearly dependent. Then we can form a non-trivial relation of linear dependence. Here's a non-trivial relation of linear dependence. Now, since it's non-trivial, not all of these alphas can be 0. Okay, it's necessary that at least one of these alphas is not 0. Okay, so let's choose one that's not 0, and that's what we call alpha t. Again, we're not sure that all the alphas will work. There might be some zeros in here, but there's at least one that's not 0. Then we take this equation, and we're going to do some algebra on it. All right? So he's kind of doing this differently. Instead of starting with this equation and manipulating, he's rewriting ut in the following way. He's writing ut as minus 1 over alpha t times minus alpha t ut. Okay. Now, what is minus alpha t ut? That's the same thing as taking alpha t in here, alpha t ut, and taking it to the other side. So minus alpha t ut will be all the other terms in this linear combination. Okay. So you see how this connection is made here? That's just rewriting this equation and putting the alpha t ut on the other, minus alpha t ut on the other side of the equation. Okay, so then, and we're using these properties of vectors, the additive properties of vectors, and so on. I'm not going to emphasize the formula. I just want to help you get the idea. Okay. Now remember, when then here you're using the distributive law to combine these constants so that each vector has its own constant, and voila, we have ut as a linear combination of the other vectors in the set S, okay, which is exactly what we wanted to show. That's what we had here. Ut is a linear combination of the vectors u1 through un, all except ut. All right, so we started with the hypothesis, S is linearly dependent, and we ended up with a conclusion: the vectors u1 through un, all except ut, have a linear combination that gives ut. All right, so that's the first way of the proof. The other way is actually easier. The other way, we assume that ut can be written as a linear combination of the other vectors. Okay. And then we take, so that means that there must be some constants that give me this expression of ut in terms of all the other vectors. And I simply subtract ut from both sides of the equation. Okay. If I subtract ut from the left-hand side, I get 0. If I subtract ut from the right-hand side, I'm going to put, I put a minus 1 ut here. Okay, so we have a 0 here, and we actually have a linear combination of all of the vectors in U. Here, the constant coefficient of ut is minus 1, just as indicated here. Okay. All right, now, here's the important point. This theorem can be used repeatedly to whittle down the size of a set of vectors using in a span construction. Okay, we've already seen this, but we'll see some more examples. If you have a linearly dependent set of vectors, you can throw out some of the vectors, at least one of the vectors, and then if it's still linearly dependent, you can throw out another one. Okay, so here we have an example. Let's consider these 4 vectors. Now, it turns out that when you row reduce, you get a result like this. Okay. All right, so let's write the solution. Now, remember, here you have one free variable. So actually, the way you get the solution is you can set the free variable equal to be anything, and then you get the other variables, right? This one says that x1 equals minus x4. This one says that x2 is equal to 0. This one says x3 equals minus x4. I'm sorry, this is minus 4x4, sorry. Okay, and x4 is undetermined. Now let's just choose any old x4. Let's choose x4 equal to 1. So that's what he does here. So this solution indicates that these vectors, the column vectors in this matrix, have the following linear dependence relationship. Right? These coefficients, as we've seen before, these coefficients come from the vector solution to that matrix equation. Okay, now look, I have a linear dependence relation here. Right? Now, just like before, I can choose any one of these vectors that has a non-zero coefficient and express that in terms of the other ones. For instance, let's consider V3. V3 has a non-zero coefficient. If I add V3 to both sides, I get V3 is equal to minus 4V1 plus V4. Okay? And the claim is that this V3 is unnecessary in the set. That if I take the span V1 through V4 and I throw out V3, then I still have the same span. Okay? So that's what we want to show, that this V3 is unnecessary, because V3 can be written as a combination of V1 and V4. How does that go? First of all, let's consider the span of just the three vectors V1 through V4. And I want to show that, and we'll call V prime the span of these three vectors. And my claim is that V prime is equal to V. That if I remove one vector, I still have the same span. So that's my claim. That's what I want to show. Now, to show two sets are equal, one way is to show that every element of one set is also an element of the other set, and vice versa. Okay, you want to show every element of each set is an element of the other set. So this is the same thing as showing that. That's the same thing as saying V prime is contained in V and V is contained in V prime. All right. You may have seen proofs like this in discrete math class. So we just need to show that both sets are contained in each other, and then they must be the same set. First, start out with this proof. We want to show that V prime is contained in V. Now that seems pretty clear because V prime is the span of three vectors, and these three vectors are included in the span of in V. Okay, so it seems very clear. So in fact, every linear combination of these three vectors is also a linear combination of these four vectors, just the V3 has a zero coefficient. Okay, so that means that just what it says, that any element of V prime, which is a linear combination of these three vectors, is by default also a combination of these four vectors. Okay, now we want to show the other way. We want to show that every element of V, which is the span of these four vectors, is also in the span of the three vectors. So let's choose any element from V. And we can express that in terms of scalars. Okay, so this V must be a linear combination of these four vectors. Okay, but I can substitute for V3 because V3 is expressed in terms of V1 and V4. So I substitute for V3, then I use my vector operation properties. I distribute the alpha 3, then I use so that I get this result. Then I use commutivity and distributivity to rewrite this V as a linear combination of V1, V2, V4. Okay, so what does that tell me? V is also in V prime because V prime contains all linear combinations of V1, V2, V4. Okay, so we're good. We've verified that once you get one vector in terms of the other vectors, you can throw that vector out and keep the same span. Now we did this for a specific case, and you can see that this argument is going to work in general. It's just a question of notation. Okay, so now we're going to formalize that process in general. Okay, we'll do more examples that show the same thing. Okay, and really we're going to do the very same process, just we're going to notice a little bit more what's going on when we throw out these vectors. All right, so let's start with this example. We have a set of 7 vectors, and we're looking at the span, and we want to see how we can systematically throw out vectors and keep the same span. Okay, so first of all, we create the matrix whose columns are these column vectors. Then the next step that we've always been doing is you do the row reduction. Notice the free variable columns, 1, 2, 3, 4 free variable columns. Okay, so you can create solutions in terms of these 4 free variables. Okay, any solution will give a relation of linear dependence, as we've been seeing many times before. Okay, these solutions will allow us to solve for one column vector as a linear combination of some of the others. And what we're going to find out, just to spill the beans, is that we'll be able to express these columns corresponding to free variables in terms of the other columns. Now, I shouldn't circle these, but I should circle these columns here. The 3 columns that correspond to free variables are the last 3 I'm sorry, and this one too, and this one too. All of these columns that end up corresponding to free variables will be expressible as linear combinations of the other columns. All right, that's what's going to happen. So let me just say that again. You start with a matrix, you row reduce it, you identify the free variable columns, and you go back to the original matrix and see the columns in the free variable places, and you're going to be able to express these columns as linear combinations of the other columns. What does that mean? That means that the pivot columns span the same span as all of the columns. It's enough to keep only the pivot columns and maintain the same span. Right? So that's what's going to be the result. Now, how do we do this? Remember, when you have a solution, you can set these constants to be anything you want. Okay? So the first choice that we're going to make is we're going to make this first free variable be 1 and all the other free variables be 0. If you do that, you'll see that this is the solution vector you come up with. Okay, I'm not going to go through that. You can look at this matrix here and verify that if x2 is 0, x2 is 1, x5, x6, x7 are all 0, this is the solution that you'll end up with. Now look at the linear combination you have. This means that minus 4 times the first column, plus 1 times the second column, plus 0 times all other columns is equal to 0. Notice that this 1 came from the free variable column. And that 1 is necessarily there because the free variable columns, I'm sorry, this 1, no, I actually said that right. Because x2 is 1, that's where this 1 comes from. So this 1 necessarily came from the fact that x2 is a free variable, and we're setting that equal to 1. Now, since that coefficient is 1, that means I can solve this relation for A2. It has a non-zero coefficient, which is 1. I can pull all the other ones over to the other side. So in fact, in this case, A2 is equal to 4A1, because when I pull a minus 4A1 to the other side, I'm going to get 4A1. A2 is a linear combination of the others. That means A2 is surplus. We can remove it from the linear combination. And so you can see here that we've now removed A2. A2 is gone. Okay. Now that worked for A2. For A2, let's try for A5. Okay. Remember that x5 was the second free variable. So let's go ahead and see what happens when we set x2 is 0, x5 is 1, x6 is 0, x7 is 0. What solution do we get? Okay, you can work that through and find out that this is the solution that you get. I invite you to do that from the matrix. We've done that many times. Now remember, this is the entry corresponding to the free variable, and that turns out to be 1 because of this. And this expresses a relation of linear dependence among the columns. So this is the relation. No, because A5 has a non-zero coefficient, I can express A5 as a linear combination of the other columns. All right, what have I done? I've just taken all the other columns and moved to the other side. This minus 2 becomes a plus 2. This minus 1 becomes a plus 1. This minus 2 becomes a plus 2. I have A5 as a linear combination of the other columns. So what does that mean? That means A5 is unnecessary in my linear combination. So notice that A5 is now gone. All right, do the same thing for the free variable x6. It's getting to be very repetitive. Do the same thing. You'll find this solution. This solution transforms to this relation among the columns. Here's my 1 here. I can solve for A6 in terms of the other columns. That means that I can throw A6 out of my fundamental set that spans. Finally, x7, do the very same thing. You've ended up with A1, A3, A4. Remember that A1, A3, 4 were exactly the pivot columns. Okay, A1, A3, 4 are the pivot columns. The pivot columns are 1, 3, 4. So again, I'm not looking at the columns in the final matrix. I'm looking at the columns in those positions in the original matrix. First column, third column, fourth column. So in fact, those 3 vectors are my span. A1, A3, A4. This is a linearly independent set of vectors that span the set. Now here's an important aside that we'll come back to later. We now have our span for the set of columns in the matrix. And let's go to Archetype I here to see what he's talking about. Okay. Archetype I. Now notice that the columns corresponded to the coefficient matrix of the left-hand side here. And apparently this system is consistent because it's possible to find constants x1 through x7 that give me these constants on the right-hand side. What does that actually mean? That means, if you think about it, that this vector 3, 9, 1, 4 must be a linear combination of the columns of this coefficient matrix. That means that 3, 9, 1, 4 must be in the span of A1, A2, A3, A4, A5, A6, A7. It's in the span. But we just showed that the span of A1, A2, A3, dot, 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 up to A7 is the same as the span of just 3 vectors. So let me go back. It's the same as the span of these 3 vectors. Okay. In fact, this vector can be expressed in terms of these 3 columns. And that must be true for any B that satisfies this system. That any B that satisfies this system must be a combination of these 3 columns. And you can show also by solving the system with just these 3 columns that such a solution must be unique. Well, we'll come back to that point later. Okay. But we're giving a more geometrical interpretation of the set of constant vectors which have a solution. Okay. All right, so let's return to the example and generalize. Okay. Remember what I said is that if you have a set of column vectors, you can form the matrix, and it's the pivot columns that turn out being the same. Well, the pivot column. I'm sorry, just say that again. If you have a set of vectors, form a matrix from these column vectors. If you row reduce and take just the pivot columns, those pivot columns will span the same set as the original set of vectors. Okay, so that's the proof. Let me just write through the. I'm sorry, that's the statement. Let me go through this again and see that you can understand this the way it's written here. So suppose that S is a set of n column vectors. Define W as the span of S. Let A be the matrix whose columns are the vectors from S. So V1 is the first column of A, V2 is the second column of A, and so on. Let B be the reduced row echelon form of A, and let D be the indices of the pivot columns. So these identify the pivot columns of this matrix that has columns v1 through vn. Okay? So now take these vectors, which are the columns of the original matrix corresponding to the pivot positions. These turn out to be a linearly independent set, and the span of the original set of vectors is equal to the span of just these columns. All right? Now, I'm not going to go through this proof in detail, because what he does here is really using general language to do the same thing that he did in that specific example. You take the free variables one by one to be equal to 1, and all the other free variables equal to 0. And that gives you a linear dependence relation for that corresponding column in terms of the pivot columns. Okay, so that's basically what this proof is. It's a long proof, but it's just a abstractification or generalization of the procedure that we did before. All right, so let's go ahead and apply this theorem. All right, so here we have a set of vectors. These are my original column vectors. I form the corresponding matrix. I row reduce. Here are the pivot columns. And according to that theorem, I know that these two columns are going to be linearly independent, and also they'll span the same set. So I'm all done. The span of T is equal to the span of S. Now, how you would show that in particular is go through that whole procedure, but I don't have to go to the procedure because I know what the end result will be. I know that these two vectors will span the entire set of 5 vectors. Okay. All right. Now, this is not a unique solution. I could have two other sets. You have some experience in showing that two different sets of vectors have the same span. It turns out that these two vectors have the same span as these two vectors has the same span as these two vectors. Okay. All right, let's look at another example. Here's the set R. So let's create an element of R. I'm sorry, here, let's create an element of the span of R at random. I can choose arbitrary constants. He just chose the first constant is 6, second is -7, then 1, 6, 2. These are arbitrary constants. Then he did this arithmetic to end up with this vector. So this is a solution. This vector is in the span of these 5 column vectors. Now we know that we can replace R by a smaller set. Okay. When you do row reduction, you have the 2 free variables, 1, 2, 3. These 3 columns are enough to span. So, in fact, I know that this vector, since it's in the span, this vector is expressible as a linear combination of these 3. Okay. How do you compute the coefficients? Well, you take the augmented matrix consisting of these columns and this constant column. You form that matrix, you row reduce, you get a solution. If I set the free variable equal to 1, then that's going to give me these coefficients. I'm sorry, it will give me these coefficients, 1, -1, and 2. Actually, if you do this directly, let's do a little more detail here. If I do this, I'm going to get, for my constants, let me call my constants alpha. This one says alpha 1 is equal to -1. Alpha 2 is equal, so I don't need to do it more in detail. These are the constants, because this is an augmented matrix. These are the constants. So I get this constant from here, this constant from here, and this constant from here. Okay, and then I have my solution, and that gives it to me. And you can see also that there's only one possible solution for these coefficients.